Imagine it's the early 1990s. The automotive industry is in a race to make engines smaller, more efficient, and much hotter. Engineers have been using standard nylon 6.6 for years for things like radiator end tanks and cooling connectors. It's the workhorse of the industry. It's tough, it's cheap, and it's proven. But then, the limits were hit. As engines became turbocharged and engine bays became more cramped, the temperature under the hood began to skyrocket. Suddenly, those reliable nylon parts started failing. In some cases, the radiator end tanks, the parts that hold scalding coolant under pressure, would literally soften and burst. Standard nylon 6.6 has a glass transition temperature that's just too low. Once it hits 60 or 70 degrees Celsius in a humid environment, it loses half its strength. The industry had a crisis. They could go back to heavy, expensive aluminum, or they could find a super nylon that could survive the heat. That search led to the birth of PPA, polyethylamide, which we now call high-temp nylon. Before we look at the chemistry of how they fixed the nylon problem, let's talk about why we're even talking about this. At Vision Miner, we live and breathe high-temperature polymers, PPA, PPSU, PEEK. These aren't just names on a datasheet to us. We've spent the last decade building these machines, the workflows, and the processes to make these industrial survivors 3D printable. Whether you're in the automotive sector, aerospace, or industrial manufacturing, if you need parts that don't fail when things get hot and chemical, that's what we do. We help you move from prototyping to real-world production. If you want to see what these materials can do for your business, hit the link below or give us a call. We're here to help you get these parts off the screen and into the real world. When nylon 6.6 started failing under the hood, the industry didn't have an answer. They had to go back to the drawing board. The materials that had worked for decades suddenly weren't good enough. Standard nylons like PA6 and PA66 were cheap, tough, and everywhere, but they couldn't survive the rising heat and moisture of modern engine bays. At the other extreme, you had ultra-performance polymers like PEEK, materials that could handle the heat but at a cost that made them unrealistic for a mass-produced car. There was nothing in between. In the late 1980s, researchers at Amoco Performance Products saw the same problem the automotive industry was running into in real time. Standard nylons were no longer enough. But the next tier of high-performance polymers were too expensive and too difficult to justify for mass-produced parts. So the challenge wasn't just to make nylon stronger, it was to redesign it without losing what made nylon useful in the first place. They needed a material that could survive far higher temperatures, absorb less moisture, hold its dimensions under load, resist automotive chemicals, and still be processed at production scale through conventional molding equipment. In other words, they weren't looking for a laboratory miracle. They were looking for a version of nylon that could keep up with nylon's manufacturability while pushing its performance much closer to the world of superpolymers. That's where semi-aromatic chemistry came in. Instead of relying only on the more flexible aliphatic structures used in traditional nylons like PA6 and PA66, chemists began incorporating aromatic ring structures into the polymer backbone. These rigid benzene rings made the chain harder to twist and move, which raised the material's thermal performance and reduced the tendency for the polymer to soften when exposed to heat and humidity. But this was a balancing act. Too little aromatic content and the material would behave too much like a conventional nylon. Too much and it would become too difficult or too expensive to process at scale. The balancing act is what made PPA, or polyethylamide, such a breakthrough. It was not just a hotter nylon. It was a carefully engineered middle ground between commodity nylons and the ultra-high performance polymers used in aerospace. In 1991, Amoco launched Amodel PPA, one of the first widely adopted polyethylamide resins aimed directly at structural high heat applications. That mattered because it gave manufacturers something they had been missing: a realistically challenged metal in under-the-hood applications without forcing them into the cost structure of exotic aerospace materials. The lineage of Amodel later moved through several major chemical companies. After Amoco's merger with BP, the brand was eventually acquired by Solvay in 2001, where it joined a broader family of specialty polymers that also included names like Radel and Torion. But Amoco wasn't alone. By 1994, DuPont launched its own heavyweight competitor, Zytel HTN, and suddenly the high-temp nylon wars were on. These materials were designed for one specific mission: replace aluminum in the engine bay. They needed to handle 200+ Celsius spikes, resist aggressive road salts and engine oils, and most importantly, they had to stop swelling when they got wet. Throughout the late 90s and early 2000s, this category expanded as EMS Gravory and Evonik entered the fray, each trying to perfect the balance of aromaticity. This refers to how many benzene rings you can cram into the chain before the material becomes impossible to process. The history of PPA was essentially a 30-year race to find the sweet spot, the perfect ratio of chemical resistance, thermal stability, and manufacturability. Today, that sweet spot isn't just theoretical anymore, it's an entire class of materials. Modern PPA formulations are highly engineered systems, often reinforced with glass or carbon fiber, tuned for very specific performance windows. Some are optimized for extreme thermal stability, holding strength well above 150 degrees Celsius in real-world environments. Others are designed for chemical resistance in aggressive automotive or industrial fluids. And many are specifically built to maintain dimensional stability in humid conditions, solving the exact swelling problem that first pushed nylon past its limits. So what actually makes it different? Why does adding a few changes to nylon turn it from something that fails under the hood into something that can replace metal? To understand that, we have to zoom in from the engine bay down to the molecular level. In standard nylon 6,6, the polymer backbone is made of flexible carbon chains. These flexible lines are held together by hydrogen bonds, which are easily disrupted by heat or moisture. This is why standard nylon wilts when it gets too hot and wet. High-temp nylon PPA changes the game by introducing terephthalic acid into the chain. This substitution adds rigid benzene rings, aromatic rings, directly into the structure. These rings act like molecular stiffeners. They restrict the rotational freedom of the chain, which pushes the glass transition temperature way up, often reaching 125 degrees Celsius up to 165 degrees Celsius. This aromatic influence also solves the moisture problem. Because the chain is so rigid and packed so tightly, water molecules have a much harder time wedging themselves in to swell the part. You get a material that keeps its stiffness and strength in environments that would turn standard nylon into a wet noodle. Once PPA was validated, it quickly proved it could go far beyond traditional nylon applications. One of the most famous wins was turbocharger air ducts. Standard plastic couldn't handle the heat of the compressed air coming off of a turbo, and metal was too heavy and too expensive to cast into complex shapes. PPA was the perfect solution. Lightweight, heat-resistant, and chemically bulletproof. We saw the same thing in cooling system manifolds. For years, these were cast aluminum because they had to withstand the constant thermal cycling and the corrosive nature of antifreeze. PPA allowed manufacturers to consolidate multiple metal parts into a single complex plastic molding, shaving pounds off vehicle weight and millions of dollars off production costs. It even conquered the world of electronics. When the industry shifted to lead-free soldering, the temperature of assembly lines skyrocketed. Traditional plastics would melt during the reflow process. PPA became the go-to for SMT connectors and circuit board housings because it could survive the 260 degrees Celsius soldering oven without warping or losing dimensional accuracy. But the real revolution is happening right now in additive manufacturing. Historically, if you wanted the performance of high-temp nylon, you were locked into injection molding. That often meant 8 to 12 weeks of lead times and tens of thousands of dollars for a tool just to see if your design even worked. Now, with high-temperature 3D printing, engineers are using carbon fiber reinforced PPA for end-use hardware. We're seeing aerospace shops print custom brackets and ducting that sit right in the middle of a jet engine's thermal zone. We're seeing EV manufacturers print functional housings for high voltage battery connectors that need to be both electrically insulating and heat resistant. Because PPA is a semi-crystalline material, it doesn't just kind of hold up. It maintains its mechanical integrity right up until its melting point. 3D printing has turned PPA from a mass production only material into a tool for rapid, high stakes innovation. But there was still a limitation. For most of the last 2 decades, if you wanted to 3D print high temperature materials like PPA, your options were limited to large format industrial systems. These machines were typically priced well into the 6-figure range, and many operated within closed material systems where users were restricted to proprietary filaments. And that's not even mentioning the optional service contracts. That combination of high upfront costs and limited material flexibility meant that while the capability existed, access was relatively narrow. Most engineers working with PPA were still relying on injection molding for production and reserving 3D printing for organizations that could justify the investment. What's changed more recently is the availability of high temperature systems in a different class entirely. Machines like our 22 IDEX V4 are built with the thermal requirements needed to print materials like PPA, but at a significantly lower price point and within an open material framework. That shift matters because it changes how these materials are actually used. Instead of high volume production or specialized environments, PPA can now be used more directly in prototyping, tooling, and low volume end-use applications. In other words, the material hasn't changed, but the access to it has changed significantly. So what I have in front of me actually are 2 parts made in 2 different nylons. This part is made in CFPA6, and this part in my left hand is made out of HTN CF25, so high temp nylon, PPA, with a carbon fiber blend of about 25%. And this is our old Essentium material, rest in peace Essentium. But what I'm going to show you is that this is a brake handle, brake lever for a motorcycle. So if you look closely with this CFPA6 part, now CFPA6, great material still, but look, it still flexes. It still has some give, and that's great for some situations, but maybe not for a brake lever, wouldn't you say? Wouldn't you say that, Joe?
Yes, not good.
So Great material. It still has impact strength. It's just not the most stiff material we could possibly use. And if we were to expose this to any heat or chemicals, then we could say bye-bye to this part. Now, this is HTNCF25, PPA with 25% carbon fill. And as you can see, it's significantly stiffer. Yeah, I'm gonna like hurt myself if I do this. It's also probably gonna explode if I do this too. But what you can see here is that this high temp nylon PPA is significantly more stiff, and I don't really want to mess up this part, but I would like to show what happens in high heat, but we'll save that for another video. Comment down below if you want to see me do that. So what started out as a fix for failing nylon parts ended up redefining what plastics could handle. For decades, plastics were seen as a compromise limited by heat, moisture, and durability. PPA showed that those limits weren't fixed. They were just a function of chemistry. And that changes how you think about design. You're not choosing between plastic and metal anymore, you're choosing where your part fits in that spectrum. With access to high temperature 3D printing like this thing right here, that decision now happens earlier at the design stage, not just in production. Which means the real impact of PPA isn't just under the hood, it's how engineers approach the problem. Not asking, can plastic do this, but asking, what kind of plastic makes this possible? And that shift is still happening. PPA was one of the first to prove it, and it won't be the last. If you're interested in what that looks like in practice, we've got more deep dives on high performance materials and real world applications coming soon. Make sure you're subscribed so you don't miss those. And for now, see you next time.